Okay, so if I show you, we just started quadratics, and we were discussing so many different things. When there were different questions coming from you, we were discussing things about, I think we discussed some things about infinity, different sized infinities, and excuse me, things like that. Okay, so this is the little summary of this topic, everything that we are doing related to quadratics. We are going to be looking at all different places where quadratics appear. So we just see what a quadratic is. So when I say just the word quadratic, I'm just reminding you, when I just say the word quadratic, what I mean is a quadratic polynomial or a quadratic expression. They all mean the same thing. So the shorter way of saying it is just a quadratic, okay? So we were first looking at what a quadratic is, and then we are going to be looking at, in this order, what if a quadratic appears in an equation? We call it a quadratic equation. Then how do we solve them? What if a quadratic appears in a function equation, in a function formula? What kind of functions are they? How do their graphs look like? We will be looking at quadratic functions. And then if you get an inequality to solve where there is a quadratic in it, how do we solve that? So we are looking at that. And then if you get a pair of simultaneous equations where a quadratic appears in them, how do we solve that? Because you have learned how to solve linear simultaneous equations where both of your equations are linear. No powers of 2 of x were involved in all the simultaneous equations you solved before. And then quadratic equations in this guise, we'll see what that is when we come to that, right? Okay, so we discussed this, and I think this is what you wrote. This is the last thing that you wrote. So any expression in the form a number times x squared plus a number times x plus a number is what a quadratic expression is. Here a, b, c are 3 numbers, and let the number a has to be a non-zero number. It can be any number other than 0. Why? If a becomes 0, you will not have your x square term. Without an x square term, it is not a quadratic. So the condition is you have to have the x square term. Now it's raining here. It was raining very heavily in the morning. I was worried that I might not be able to have the class because it was thundering and lightning. Now it looks like it's going to start raining again. You let me know. Now I hear a big noise because of that, the noise of the rain. I hope you don't hear it. You let me know if it is a disturbance to you. Okay, there's nothing I can do about it, but you just let me know if there is anything with regard to the voice that you are hearing from my end. Okay, so the numbers b and c can be anything. It can be even 0. So you can even not have the c term and the bx term. You can only have the x square term. Still, it's a quadratic. So at least it has to have the square term. At most, it will have all these 3 terms. Okay, that's what we discussed. And then some examples. I have given here 5 examples. In the first example, I'm showing you what the a and the b and the c are. So a and b are the coefficients of the x square term and the x term, and c is just that your number. And then some more examples I have written, and these examples are given you to show that your quadratic, all these are quadratics, but they might look a bit different. I have jumbled up the terms. You will not always have the x square term in front. You can always, move the terms around and rearrange it to give that form ax squared plus bx plus c. But it can be all jumbled up. And some of these terms have only, some of these quadratics have only the x square term and the x term. Some have x square and the number term. Some have all 3. Some have just the square term. Okay, so I have given you all kinds of different looking quadratics with different combinations of terms. So I don't think you copied this. So can you copy these examples? Or let me know if you already copied this, because this is where I remember that I stopped. So while you're writing, let me remind you, for anyone who, especially for Umasha, if you have any question, Umasha, you just unmute yourself and you can talk to me, or you can drop a message in the chat box. That's how we communicate. Okay, I prefer you talking to me. Anyone, when you have a question or when you have something to say, it's easy if you can talk to me, because I readily hear you then. Because if you drop a message, I have to go and open the chat box to see it. So that kind of disturbs. But it's your preference. It's whatever is comfortable to you, you can do. And when you are done, copy.
No problems.
Umasha?
I have no problems.
Okay, okay, that's good. Whenever you have a doubt, a question, anything that you don't understand, you have to quickly tell me. So, okay, Masha, because as I always tell you, especially in this mode, I have to completely rely on what you tell me, because I don't even see your faces, right? So that's a huge disadvantage in this mode. There are many advantages, but the biggest disadvantage is that I don't see you. I don't see your faces. So I don't get that feedback from your facial expressions, whether you understood or not. If you were sitting in front of me, I could see it from your faces. But now I can't. So I have to completely rely on, I have to trust you that you will tell me if there is something that you are not clear with. Okay, so please keep that in mind. And please let me know. So the other thing is, when we write a note, a couple of you have to let me know when you are done, so that I can proceed, because I can't see you and I can't see whether you have finished writing. Masha has finished writing. Yes. Also, Pesandi. I'll wait for one more person to finish and then I will proceed.
I'm done writing.
Okay, Afra. So when like 3 of you are done, I assume that all of you are done. That's how we, that's the practice. Okay, right. Now, we are going to see different forms. These are called forms. Different forms in which you can express a quadratic. Now, ax squared plus bx plus c, this form, it is also a form. This is the form that we like normally see a quadratic in. This form is called the standard form, because it's a standard. You can see the 3 terms all laid out nicely. It's all like this. It's a standard, the conventional form of writing a quadratic expression. But there are 2 other forms that you can write a quadratic in. Okay, so altogether there are 3 different forms in which you can write a quadratic. It is like, these forms are like, you know, even when you take like people, like you can take different forms. For example, like depending on how you dress up, your form could look different. You can look really casual if you're wearing sandals and a pair of what, jeans and a t-shirt. You look, that's a casual form. And you can be dressed in a very professional attire, so that's your professional form. You know, you can talk about, even for people there are different forms. Same person can be in different forms depending on how they are dressed up. Similarly, if you take a quadratic expression, I can like dress him up or dress her up like in different ways. I can change how this expression looks like. Same expression, but different forms. So there are 3 different forms in which you can write a quadratic expression. So as I said, this form, when you have the 3 terms all laid out nicely, like all 3 terms separately laid out, the x square term, the x term, and the number term. It's called the standard form. There are two other ways that are called factorized form and complete square form. When you take a quadratic expression, I think I got stuck. No, okay. When you take a quadratic expression, now the first form I have shown here is the standard form. What is that? When you have the expression in the form ax squared plus bx plus c. And the second form is called factor. You already have learned this. Okay, I'm kind of putting it into a framework for you, so that you have it in the knowledge that you already have. I'm organizing it in a certain way, right? So standard form, and you know that certain quadratic expressions can be factorized. Now I said certain, not all quadratics can be factorized. I'm sure you have come across this. You know that when you have to solve quadratic equations, just go take your memory back to those things that you learned in O-levels. Think of a quadratic equation. You know that in a quadratic equation, you have a quadratic equals 0. It's an equation, right? Now that quadratic, one way of solving a quadratic equation is by factorizing. And if you think about that, you know that a lot of quadratic equations that you have come across, you can factorize, but there are some that you can't. So this is another way of writing a quadratic expression, but not all quadratics can be written in that form. Okay, so what do you mean by factorized form? That is when you factorize your quadratic, and then you will have how many factors? 2 factors, like in the form x minus a number times x minus a number. Sometimes you can have a number in front of the x also. Okay, I've written here the simplest form that you get. X minus alpha, x minus beta. Everything that I've written in red are just numbers. Okay, I'm writing in general how the form looks like. So factorized form is the second form in which you can write a quadratic, but you have to keep in mind, not every quadratic can be factorized. There might be certain quadratics that you can't factorize. And then third form is called the complete square form. Again, I think you have learned this in your O-levels. Can someone quickly let me know whether you have learned this?
Yes, miss.
Yes, right.
Yes.
So it's the complete square form. That is when you write your quadratic with a complete square. Now, I don't know whether I know you have learned this before. So I'm assuming that you know it very well and you have understood all this. But if you want me to explain something again, there is no problem. You just have to tell me and I will explain. Okay. So the complete square form, what do you mean by complete square form? It looks like this form. Here I have written it. This is the form, right? When you turn a quadratic expression into complete square form, it takes this format. What is the format? X plus a number square. So there is a square term. All the x terms have gone into a square term and a number plus n. Okay. And the nice thing is any quadratic can be turned into complete square form, not like the factorized form. You tell me any quadratic expression, I can write it in complete square form. If I give you any quadratic, you can write it in complete square form. Before you copy this down, just to give you an analogy of these 3 forms with numbers. I hope you know what an analogy is. Analogy is like what's another word for that? It's something like an example to understand something better. If I give you a similar example, here's an analogy to understand these 3 forms. With numbers, I'll take an analogy. I'll take an example. Say you have, think of the number 12. Okay, here's number 12. I'm going to number 12. So it's just number 12. It's written in, I'm just giving remember, it's just an analogy. So when you write 12 as 12, it's the standard form of writing 12. Just the normal way of writing 12 as 12. Here's another way in which you can write 12. You can write it in factorized form. There is nothing called that with numbers, okay? But I'm showing you even with numbers, you can think about these different forms. I can write 12, the same number 12, I can write in a factorized form. If I write, I have written 12 as a product of two factors. It's the same way that you write a quadratic as a product of two factors, right? Can I write 12 as a complete square? Right, like in a complete square form. So I have to think, is 12 a complete square? 12 is not already a complete square, right? But can I write it in terms of a complete square? What do you think? This is the same thing that we do with quadratics. What do you think?
Yeah.
Yes, how? Now 12 itself is not a complete square, you know that. What are complete squares? Do you know what complete square means? 9 is a complete square. It's a square of 3. 16 is a complete square. It's a square of 4. 25 is a complete square. It's a square of 5. So 25 can be written as 5 square because it is already a complete square. Now 12 is not a complete square, but I can write it in terms of, I can bring in a complete square into it and write 12, including a complete square in it. Can someone tell me how I can do that? How should I do that? Now, so this is like the standard.
Is 4 square minus 2 square?
4 square
I mean, 4 minus 2 in bracket, 4 minus 2 square.
Let me see somebody. So Neunaka says 3 square plus 3. Okay, let me write that also. And Aisha was saying, wait. Let me write what Aisha said first. Aisha says 4 in brackets. What did you say, Aisha?
4 minus 2 square.
Like that? Like that?
Yes.
That is 0. What did Neunaka say? Neunaka said?
No.
Did I write it wrong? Okay.
Yeah, whole thing in brackets.
Whole thing in brackets. Wait. Now y'all are giving me a lot of different ways in which you can write that. This is nice. What do you mean the whole thing in brackets? Aisha, now the other thing is you can chip in and write on the same board that I'm writing on. Y'all can write on the same board if you have that facility. You all have like with your finger you can write if you're using a touch screen device, I think. Aisha, if you have that, can you write on the board? I will erase this. What you meant? If you can write. Till that, I will write what Neunaka says. 3 squared plus 3. 4. It's okay, Aisha. Yeah, go ahead. I'll minimize this. 4 minus 2. But that is not 12. That is 4. Okay, and Senith is writing his. Is that Senith? Who's writing now?
Miss me.
Now, when you say miss me, I don't know who, because I just hear your voice.
Miss, I'm Afra.
Afra, okay. Afra 2 square plus. Yeah, that works. But 4 plus 7 is 4 plus 7, 12. 4 plus 8, would have to put an 8.
Sorry, Miss.
Yeah, right? But I hope you can see what we're trying to do here. We're trying to express 12 by bringing as with a combination of between a square and another number. So this Neunaka's answer? 3 square, that is 9 plus 3, that is 12. Or 2 square plus 8. Right? This is wrong. And then Tenumi says, yeah, 3 square plus 3. Aisha says 4 minus 2 to the power of 2 is wrong, Aisha. 4 minus 2 to the power of 2 is 4 minus 2 is 2. 2 to the power of 2 is 4. So it's not 12. Right? You have to get 12. So we are writing 12 in different forms. Okay, so this was just to show you that even with numbers, now even we don't think about this, but even with numbers, we do that. We can do that, right? Now, if you take and Senithu 4 to the power of 2, yes, Senithu says 4 squared minus 4. Correct. That is another way. So actually, when it comes to numbers, there are many different ways in which you can write it as a complete. Like if there is a complete square form, there is nothing like that with numbers. We don't do it. We don't do such a thing with numbers because there is no usage in that. There is no, if there is, we can do it, right? And if you take like 16, right? The number 16, that's a standard form. You just write 16 as 16. Here's a factorized form, 8 times 2. Factorized form, 8 and 2 are factors of 16. And here's complete square form. It is already a complete square. And there is the number 16's complete square form. Okay, it's the same thing that we do with quadratics. So if I go back to now the note, I just wanted you to have that, you know, to understand that this is something that, you know, it's not something very alien. It's something that we can even talk about with numbers, right? So when you have a quadratic, you can try and write it in factorized form and complete square form. Can you copy this? Oh, before you copy that, this last sentence I have written here. Now with quadratics, now with numbers, we never kind of learned it as a strategy that we can do with numbers. When you have a number, it's useful to write a number in factorized form. And it is useful to write it in the complete square form. We didn't learn it like a strategy to do things, right? But here we are learning it as something to remember. Why do we talk about this? Why do we give it importance here? Why do we say that a quadratic can be written in these 3 forms? Because each of these forms has its own advantage. When a quadratic is written in these different forms, each form gives you a certain information about the quadratic. We will see this later, but after you copy this, I might talk a little bit about it right now. It can be easily seen when we go to talk about quadratic functions. But even now you can see it. These different forms tell you certain important different things about the quadratic expression. Okay, so each form has its own advantage. Having written in that way gives you a certain set of information about the quadratic. It's like when a person is dressed casually, you can, by looking at that, you can get some information about that person. When he's in professional attire, you can get some different information about that person. The way that, you know, I'm just trying to again, that's another analogy. So just like that, in different forms, when a quadratic is in different forms, each form tells you something about the quadratic, which is useful. That's why we learn about these 3. Okay, now quickly copy this. And we have to learn how to change one form to the other form. That's what we will be looking at next. And actually, can I add something here? Let me add an example here. Under these, I hope you didn't come to this line before you write. No, after you write that line, let me add a line here. Let's write an example. Okay, and I want you to write, I will give you a quadratic in standard form. You write the factorized form. Here's the standard form. Put it in the next line. I'll give you one in standard form. Okay, and can you write it in factorized form? And complete square form. Okay. Now I'm doing things here. I hope I'm not blocking your view of the note. Right. Okay, so this is now I have put a capital Q when I hope you remember this. With the capital Q, that's like an abbreviation that I use to stand for quadratic. Okay, to save space because I can't write all that here. I'm using a capital Q whenever I want to say quadratic. So when you are done, I have to move the screen. Okay, I'll make it a little small. Sorry about that. Okay, now you can see the last line. So when you're done copying up to that last sentence, you let me know. Let me say here about the Q, about the quadratic. The last sentence is each of these forms provides a different set of information about the quadratic. Okay, then is done. I'll wait for 2 more.
Done, miss.
Okay, Aisha is done. Nisaki is done. So I'm going to move on from this. If anyone is still writing, you please let me know. Now, as I said, each of these different forms tell you something about the quadratic. Let me just show you, demonstrate that to you. Okay, I'm going to take this exact example. Now, I hope, did you write this quadratic that I gave you in the example? I gave you in the standard form. Okay, Neonaka, you are still writing. So
Miss, I'm still writing the last line.
What was that?
Miss, I'm still writing the last.
Okay, Afra. So I'll just talk until then. So in the example, I gave you a quadratic in standard form. And were you able to write it in factorized form? So what do you get when you write that in factorized form? So now this is something that I expect you to be able to do. That's why we did prerequisite algebra. You all have to be able to factorize this quadratic in one step. You have to be able to write the factors in one step. I have started to write by opening a bracket. So it's x. I hope you know what to do. You think of two factors of, yeah, let's see Senitu. CSF, right? Let's see what the CSF should look like. So the factorized form is, you have to think of two factors of 8 that add up to plus 6. Two factors of plus 8 that add up to plus 6. That would be plus 4 and plus 2. So plus 4 and plus 2. That's the, oops. That's this quadratic in factorized form, right? Then complete square form. I hope you know how to do it. So you open a bracket, you're going to write the complete square here. X, so the middle term is 6x. You have to take half of that plus 3 square, oops. And then what you will get is minus 9 plus 8. That simplifies to plus 9 minus 8 is minus 1. So I will just write minus 1. Okay. So this is how you write that example quadratic that I had given you in standard form, in factorized form, and in CSF form, complete square form. If anyone is not clear with any of that, you have to let me know. So I will just show you what are these different information that they provide in these different forms. This is what I mean by this, okay? Now I'm going to go to the whiteboard. All right, okay, Umasha. Let's see how this complete square form, how we write a quadratic in complete square form. Now, let me clear this. Right, let me change this to this mode, right? Now a complete, okay. If you have something like this is a, now in numbers, we saw that 16 is already a complete square. 9 is already a complete square. So you know what complete squares are in numbers. A number that has a perfect square or a proper square root, right, is a perfect square. So these are perfect squares. Same meaning complete square. We call this complete square because we are completing a square in that. Okay, we are writing it in a way that it has a perfect square. So it's a process. That's why it's called completing. You're completing it into a perfect square. Now, like that, like you have 16, 9, 25, 49, and so on, perfect squares with numbers. There are perfect squares in quadratics. Here's one. Something like 2 squared. You mean x squared, right? Afra?
Yes, miss.
If the equation is something like x squared plus 3x minus 7. Now, Afra is asking whether this is already a complete square. I mean, already a perfect square. If Now, if something is not a perfect square, you can complete it into a square. 2x square. What do you think? Is this a perfect square already? It's not written in that form, but is it a complete square already? Afra is asking, can someone answer? How do you see whether it's a complete square? Something is a complete square. Now, let me again, it's the best way to understand something is to understand the concept with something that is simpler to work with. Like, go back to numbers. Forget these expressions, go back to numbers. Now, 16 is a complete square. Not a complete square, is a perfect square. It's a perfect square. So there is nothing to complete in that. It's already a perfect square, right? So if I write it in square form, 4 squared. It's already a perfect square, 4 squared. But if I have, say, 15, it's not a perfect square. So I have to complete it into a square. I can complete square. I can do the completing square process to it. What should I do? It's 1 short of a perfect square. It's 1 away from 16. 16 is a perfect square. Now I have 15. It's 1 short of 16. So what I can do is I can add a 1 and minus a 1. Did I change the number that I had, which is 15? Is it still 15? 15 plus 1 minus 1. Is it still 15? It is still 15. Now why did I add a 1? Because it was 1 away from the 16. Now, if I take this, that is a perfect square. So that I can write as that. Now I just completed the square. So I have written 15 as in terms of a perfect square. So that process I did is, I completed the square. The process is called completing square. And this form you can call complete square form. Okay? Is that clear how you do that with numbers? It's a similar thing that we do with quadratics. So certain quadratics are already perfect squares. What do you mean by that? So if I have I will write a quadratic in factored form. Think of something like this. That's a perfect square. Doesn't it look like this? It's the square of the same factor. X plus 2 times x plus 2. It's the square of x plus 2. So if I expand this quadratic and get its standard form, it is a perfect square. And here I have written it in the perfect square form. So if I expand this, what is this quadratic actually? It is, let me write it in different color. This is x squared plus 4x plus 4. Here is an example for a quadratic expression that is a perfect square, just like 16 is a perfect square in the number world, which that you can write as 4 squared. So this quadratic expression can be written as this: x plus 2 square. It's a perfect square, right? So this is an example for a quadratic that is similar to 16 with numbers. This is a perfect square quadratic. This is a perfect square number. Now, what we are doing here under completing square is, if you have any other number, if we go back to number world, if I give you any other number which is not a perfect square, I can still write it in terms of a perfect square, like I did here. That process is called completing the square. And this form is called complete square form, right? See, a similar thing can be done with quadratics. So in a quadratic, let me erase this. So let me take a quadratic that is not already a perfect square, like the one I had given you in the example. What was it I gave you? Now I'll go to a new page. I gave you x squared plus 6x plus 8. Okay. Now this is what you do. Here's the strategy. Now I'm going to write this as a perfect square, but I will have an extra number here, just like when I was writing 15, because I had to add something to it to make it into a perfect square. but I have to subtract it back because otherwise I would be changing the original number. So I have, in effect, I have added here a 0. I have not done anything. I add something and I take it away. So that's same as adding nothing, right? But when I think about 15 plus 1 separately, that gives me a perfect square. So there, this is 16 minus 1. So that I was able to write it that way, right? Similarly, so here's your perfect square, and there is a hanging little extra piece there because you completed a square here because it was not already a perfect square. So even here, when you try to turn this quadratic expression into a perfect square, you will have something like that, but plus or minus a number also you will have, like extra number hanging there. Okay, I'm going to now explain this to you in a different way. I think no one may have seen this before. I know you have learned how to do this in O-levels. As a procedure, let me give you a graphical explanation to this. Okay, let me give you a graphical explanation to this. I hope you all will like this. Now let me start with this x squared plus 4x plus 4. Now just forget everything else and just focus on what I'm going to say now. Okay, look at this quadratic expression, x squared plus 4x plus 4. Now you already know this is a perfect square. Now I'm going to give a graphical meaning to this. What's the meaning of square? Now just think about it. You call it completing square, perfect square. It has this word square. Isn't square a geometric shape? Square means that, isn't it? What does that have to do with this? Why have we taken this that word? You know that the power 2 is also called square. But what is the connection there? Why do we call it? Why are we using the word square for power 2? Did you ever think about that? Now, no. in the Sinhala language, it's not the case. In Sinhala language, square means sama chaturasraya. And when you take the power 2, you call it varga karanama. If you wish, I'm sure you all speak some Sinhala. And so in Sinhala, for how do we say this? X vargaya. That's how you say it. You don't say X sama chaturasraya. But in English, this is called X square. We use the word square for it. Why is that?
Because when you find a square, the area, you have to multiply both the same number, like 2 into 2 or 4 into 4.
Right. Yes. I think what you're saying is what I'm trying to explain. It's because this. Now, you remember that whenever you have a product of two numbers or two things, product of two things, okay? Whenever you have a product of two things, it can be thought of as a rectangle. Here's what I mean by this. Say you have 2 times 3. You know the answer is 6, okay? This 2 times 3 can be thought of as a rectangle whose side lengths are 2 and 3. And the answer to this is the area of this rectangle. Does this work for any product? Yeah. 5 times 9. 5 and 9 rectangle. Area is the answer. 9 times 5 is 45. Right? So any product between two things, the answer to that can be thought of as the area of a rectangle whose side lengths are the two numbers that you are multiplying. Then if the two numbers that you are multiplying are the same number, like 2 times 2, what you get is the area of a square, right? Isn't it? So if you have 3 times 3, you're talking about the area of a square whose side length is 3. This is 9. The area of that square is 9, right? Okay, now keep this in mind, okay? Whenever you have a product, two things multiplied, you can think of it as representing some area of a rectangle. If you're multiplying the same thing, it's a square. Then I'm going to erase all this. Okay, now I said, oops, I think, okay. Sometimes when I like erase very fast, this gets stuck. Now I said that this expression x squared plus 4x plus 4 is a perfect square. Let me write that word here. Now you will see why it is called a perfect square also, that why we say it's a perfect square. I'm going to represent this expression as a picture. Let's go to each term. Look at x square term. Graphically or diagrammatically, or like in terms of a picture, what does it mean? X times x, it's the square. It represents the area of a square whose side length is x. Is that right? So x square represents a square. Area of a square. Do you all get that? Okay?
Yes.
Yes. Then let's go to, now I have to add to that 4x. 4 times x. That's the area of a rectangle whose side lengths are 4 and x. Right? So if I draw that, again, I'll use a different color. So now x I have taken to be this long. So x is something that is unknown. So I've taken it to be this long. So 4x would be, okay, I will draw another one. So I have to add to this. I will draw it adjacent to this. Like starting from here, that is x long. And suppose this is what 4 is. So now you have to assume that this is 4 long and this side is x, correct now? Because it's the same length as the x, okay? So this is the 4x term. Let me write that inside each of it. This is the x square. That represents the x square term. This represents the 4x term, right? Now the term 4, the last one. So I'm drawing a diagram to represent this expression, okay? It's just 4. I can think of it as 4 times 1, isn't it? 4 times 1. Now, before I add that term into this diagram, I'm going to do something. Now, I said that this is a perfect square. It's x plus 2 square. We know that, right? Where did we get it from? Here, right? X plus 2 squared. We know that, oops. Okay, right? I'm going to do something before I add. Now, I still have to add this term 4 by thinking about it as 4 times 1 or maybe 2 times 2. I can add another little square to it, okay? But let me not do it right now. Let me just leave it. I'm going to make a small change here. Now, this 4x piece, the 4x piece, think of this as pieces, right? I have the x square piece, and then I have the 4x piece. I'm going to do a little trick here, do something here, because I know that when I finish drawing this, I need to get a perfect square. This is what you're going to see. Now this 4x, I'm going to split right in half. You will see why I do that. I'm going to cut this right in half, okay? And I'm going to bring this part down here. Can I do that like this? It will perfectly fit here now, because it has, this length is x. And then, I don't know whether, so I'm going to redraw it. I don't know whether I'm like making it, because if I wish I could draw this like in a real board. Now I will, I'm going to draw it again here. This is your x by x. So this is your x squared. Now that 4x piece I cut in half, and one part of it I'm going to leave where it was, right here. Like that is half of it only now, okay? So this is x long, and how long is this now? What's the width now? Because I split it in half. It was originally 4, Now it's only
2.
2. Now this is too long, right? And the other piece, I'm going to bring down and fix here. It will perfectly fix here, right? Because this is x long. So this side came now here, and this would be 2 now. Did you see what I did? This other piece I brought down and fixed it there. Okay. Now, this little piece, let me draw in a different color, green. What's the area of that? What
4
are the
into 2, 4.
That's a 4 because 2 into 2. This is 2, this is 2. It's 2 by 2. This is a 4, and that's what that is. So these 3 terms make a perfect square. It represents the area of a perfect square. For any quadratic expression, which is a perfect square like that, you do it later to experiment. By moving the pieces around, you can form a perfect square. Now, what we do when we have an expression that is not a perfect square is we try to complete the square. So let me show you that. Now, the example that we had was x squared. Now, I'm taking the example that you did, plus 6x plus 8. Now, I'm going to draw the diagram for this. Here's my x square term. Now, this is not a perfect square. If I put this into pieces, it will not make a perfect square. So I have to complete it by adding extra pieces, and I have to do something and make it into a perfect square. So let's see how we do that. Here's the x square term. Suppose this is x long, so that will be the same length. I call it x. So this piece, that's the first term, x square term. This is the x square. This represents the x, this part. Okay, this part. Now plus 6x. Plus 6x, luckily because it's 6x, it always fits here because one side is x. So it always fits nicely along one side of that square because it's x long and 6 wide. 6 wide, it's 6 wide. Suppose that is 6, suppose this is 6. So this is x long and 6 wide. Okay? Now what I do is this, I just take those 2 terms. So I have these 2 pieces. I want to make a perfect square. I'm trying to complete a square. So like what I did earlier, I break this into 2. I break this right in half like that. So I will draw this again. I'm showing you what I'm doing there. So that means I have this thing. And then I break that piece right into 2. And then leave one right there and bring the other one down. Okay, so I have this here and this this piece is what that is. What that is. It's not writing. Okay. Now let me write the dimensions. This is x long from here to here. This is x long from here to here. Oh, I forgot to tell you something. Can I go back to the previous? I'm sorry. Oops. Oh, where is that? Oh, here. Now I'm sorry. Okay. Now this was already a perfect square, right? Now see what happened. Now all the terms nicely fitted into this square. Now how can you write the area of this square? Side length times side length. What is the side length here? X plus 2. X plus 2. And this way, x plus 2. That is why this is equal to x plus 2 times x plus 2 is x plus 2 square. So that gives you a complete perfect square. Okay, for that expression. Now here, we are trying to complete a square because you will see it's not a perfect square. Right, now what did I do? I broke this into 2. So how long is this piece right here? What's the length of that? 3.5 of 6, because that 6 length got cut by half. So that is 3. This is 3 long and this is 3 long here. It's the same piece there. These 2 pieces are identical. This piece and this piece, they are identical. Now in order to make this into a square, I need one more piece. I need to fill this up. Now don't forget, I still have this 8. I can make use of that. I can put it to somewhere here. It's like jigsaw puzzle. Now, if I can fill that up, I have a perfect square. How much I need to fill that up? Now I have 8 left in my hand. I still have this to put into this diagram. Okay. Out of the 8, let's see whether I need the whole thing or I am short of something. How much do I need to put there in order to complete a square? What are the lengths there? 3 and 3. So I need a little square piece that is of how much of area? 9. 3 times 3, right? This is 3. This is 3. I need a piece that is 9. But I don't have 9. I have only 8. This 8 piece, this I could have drawn as a 8. I could have drawn 8 as a piece that is of 4 by 2, or how else? 8 by 1. No, a long piece. Oops. Like a long piece that is 1 breadth and 8 long. These are different ways in which I can think of 8. Because this area represents the 8, right? That this is also 8, this is also 8. Now I need to put here a piece that has an area of 9. What can I do? I already have 8. I can, my expression is x squared plus 6x plus 8. So you can see that I'm short of just 1. I need a 9 here. I'm short of a 1. So what I can do is I can add a 1 and minus a 1 so that I have my 9 here. Okay. So when I have my 9 here, I can put that as a piece here. But take away 1, I still have left minus 1. And this is extra now. This is extra. But with this, I made a complete square. And what's the area of that? What's the side length of that? X plus 3. X plus 3 times x plus 3. X plus 3 times x plus 3. The two sides are. So that is x plus 3 squared. And I will have that minus 1. That got stuck there as part of what I did. Because I had to add 1 and minus 1. This is why this process is called completing a square, because you're trying to complete a square with these terms. If these terms represented pieces of little area pieces. I don't know whether you like this, but this is the best. This is from where this word completing square comes, because what you are graphically or in terms of a picture, what you are doing is you are completing a square. So if some quadratic expressions they already represent a square, nothing to complete, it is a square. So they are called perfect squares. So you can write them as square of some expression because it is already a square. But for certain other quadratic expressions, when you do the complete square, you get that little expression with a hanging number, because you have to adjust. You either have to add you need something extra, or you will end up with something extra. Afra says, is this graphical representation applicable for my question I asked? Which question, Afra? Which question you have asked? Is that you writing up? Senator is asking, Miss, if this is a quadratic equation, can we differ the square by the values we find? What do you mean by that? What do you mean by, can we differ the square by the values we find? What do you mean by that? Senator, can you speak to me? That will be more effective than writing. No, I don't understand what you're trying to say by saying differ the square by the values we find. Senator, are you able to speak? Unmute and speak. It will be fast and it will be more. Oh, mic error. Okay. Now that's the other thing. Okay, all of you have to somehow try and fix your mics. Make sure that your mics are working. Then it will be very easy to communicate, because you otherwise you have to type, I have to read, there will be typing errors, and I have to go back up and see what you have typed. I can miss what you type, because when a lot of you are typing at the same time. So if all of your mics are working, this will be very productive. Okay, who's writing something here? 2x squared plus 3x minus 7. I think this is Afra. So what's the question now, Afra? You're asking, is this graphical representation applicable? For this? Yes, of course, it is.
How many?
It is applicable to anything, but there is a little small thing that I not cunningly, I avoided negative terms. Now you might ask, if I have x squared minus 6x, what does because I kept adding pieces to this, right? But if you have a negative term, does that mean, so you will ask, does that mean do I remove a piece? You don't remove a piece. You think of a negative term as then it becomes a little complicated, not very complicated, but if you're not familiar with this thing, it becomes a little complicated. Negative terms have to be thought of as, with numbers it's okay, minus 7 is okay, but like if you have a negative x term, that has to be thought of as positive and negative we think of as opposites, like matter and antimatter. Matter and antimatter, the meaning of anti? In science, in physics, we talk about, for any matter you have, there is an antimatter, the complete opposite of this. So if you put the two together, a matter and a piece of matter and its antimatter, if you put them together, they annihilate and they vanish. You get nothing. Similarly with numbers, if you have a number and its opposite number, which is negative number, when you put them together, that's why you get 0. Like 3, that means positive 3. If you put negative 3 and positive 3 together, they vanish each other, right? And you get 0. So in that sense, we represent negative terms with like we take opposite colors like black and white to represent positive terms and negative terms. So that is something like that we do. I will not go into that. We will not be able to finish the lesson. But somebody made it +7.
Can you please write this in the complete square form, because I actually go wrong in this.
Right. Okay. So I will tell you why it is harder to write this as a incomplete square form. When you have a number in front, when you have a number in front of the x square term, this strategy fails. So you first have to get rid of the 2. So I will show you. No, wait. No, so I will actually show you. Okay. I will. I think okay. So the expression Afra gave me, was it Afra? I think so. 2x squared plus 3x plus 7. Before I do this, let me take one more example with a normal x squared term. Let me take a different. Let me take something like. Oops. Okay, let me take this. Okay. Now this is for Umasha. Umasha wanted it. It was her request originally to explain. Now let me just show you how to do this, like step by step. Like you can't be drawing all this to do it, right? That's not how we do it. But have that picture in your mind, what you do. Okay, then it's easy to think about this. Take this x squared plus 9y plus 20. Suppose I want to write this in complete square form. Okay. Remember, so just like when I was doing with these pieces thing that I was doing, I was working with these two pieces. The number I looked at in the end, do I need it? Or do I need part of it? Do I need more than that? Like, okay, the number 20 is there to fill in the last bit of little pieces. I try to complete the square with the, what is this, y? It's not y, it's x. Oops. In black. Okay. oh no, let me take a nice number here, not 9, let me make it 8. 8x, okay? We will take something like 9y later, 9x later, okay? So you look at these two terms, okay? Now visualize that diagram. So x square already, this first term is already a little square piece. And then 8x is here, you split it into 2 and keep half of it here and take the other half down. That gives you your side length of your square. That's how you always complete the square using these two pieces. And then finally you try to fill in that little box that is left here. That is the process that you do. So if you keep that visual in your head, your square finally ends up with, what is the side length? X plus how much here? Tell me, x plus how much here? Half of the 8x, so x plus 4. X plus 4. Where did the 4 come? Because you split that piece into 2 and leave one there and bring the other one down. So one side becomes x plus 4 and this side also x plus 4. So your square is going to be x plus 4 square. So this is your x square. I'm just trying to, when you do this, you keep this picture in your mind. This is these two make up your 8x. And then this piece right here, let me do that in green. That's the piece that you fill with the number that you have left there, 20. 20 might be enough, or 20, you might not need all of that 20. So let's see. So how much is that? Or I'll tell you, there are two ways of doing this. You completely forget the 20. Okay, you completely forget the 20. Let me write this 20 on the side. Let me move it. Let me move it to right here, plus 20. It's there, but let's just forget it for now. Now look at these two. I've written it like this, right? Now, when I wrote x squared plus 8x as this, I have already included this piece in this expression, isn't it? So I have to remove it. I have to minus this piece. How much is that piece? 4 by 4 piece. That's a 16. And then you will have your plus 20. You will have your plus 20. So finally, your answer is going to be, your expression is going to be x plus 4 to the power of 2 minus 16 plus 20 gives you plus 4. That's how you complete your square. Yes, I don't know whether you.
This is plus 4. Can we draw another square like 2 into 2?
Yeah, but that is not needed. Our aim was to put the terms that have x in them, like the x square and the 8x, into a square. So that is done. Now all the x terms are in here, right? And they are inside a square.
Yes, but if the coefficient was not 1, and what if it was like 3 or 2?
Yeah, so I will come to an example like that. But still before that, let me take, now I will go gradually towards the difficult ones, okay? So first, is this clear to Umasha? I will do one more when this doesn't divide by 2 exactly, okay? Say you have x squared plus 7x plus 3 or something. You can write anything that comes to your mind. With anything it works. And suppose I make this minus, not plus, minus now, okay? This is what you do. Okay, Umasha says it's clear. Let me quickly do this. Now what you do is you focus only on these two, forget the plus 3, okay? Keep it on the side. Don't look at it right now. So you have to now write this as, this is going to be x minus half of 7, because you split that 7x piece into 2. So that's going to be your side length of your square. So half of 7 is, you can write it as 7 divided by 2, or you can write it as 3.5. Doesn't matter which way you write it. Let me write 3.5. No, let me write 7 divided by 2. So same sign, whatever the sign here comes here, okay? Because now that piece is a black piece. It's only the color changes. So this is the same sign, square. And then there is an additional piece that you have added that, so you know, right? Like it only makes something like that. But this also you have included in this expression. So you have to minus it. Minus, what do you minus? What's the side length of that? That is a side length, the square of that. Because this is 7/2 and that is 7/2. So you have to remove that. Is that clear? And you have the +3. And then finally, x minus 7/2 squared. This is whatever, 49/4 +3. And then you can combine these two to a single number if you want. I mean, you should do that, right? So it can get ugly when this number doesn't divide by 2 exactly. One more I will do before I go to an example with a coefficient in front of the x squared term. Let's take x squared minus 10x plus 3. How do we do this? You only focus on these two. X minus, same sign here, take half of this number 5 square, and then you minus that little piece, 5/5 piece, that is just 25. So it's actually square of this number, 25. I can straight away write 25 here, minus 25. It's always minus 25. Why are you minusing it? Because this expression has that additional piece. You have to remove it to be equal to the original expression, and you have your +3. So this is x minus 5 squared minus 25 plus 3 is minus 22. That's your complete square. Okay. Now
Miss?
let's, yes.
Miss, since there's like a minus 22, when we draw the square, when we take away minus 22, does it become a square?
Say that again.
Like the graphical representation,
Yes.
like if we remove 22 away, it doesn't become a square. So it
No,
does.
so this part represents the square. This is your square. That is what your square is. This is an extra piece. So you are not actually, it's like it's like now with numbers, when you had, say, when you are, if you want to write 17 as a in terms of a perfect square, you can write this as 16 plus 1. So that is 4 square plus 1. This is the perfect square. Plus 1 is just hanging there. It's additional.
Oh, I got it. Thank
Got
you,
it?
Miss.
Right.
Yes.
Was there another question? Senitu, Miss, could you give a question with a coefficient to the, yeah, to try alone without me explaining first? Senitu, you sure? No, I'll show you one, okay? Because you can't do this completing square process if you have a number in front. Because the whole thing, if you think of the graphical thing that I did, you always started with the x square piece. You need that to start with. To that piece, you attach little other pieces symmetrically to form a bigger square. So you have to start with the x square piece. It has to be an x square piece. If you have 2x squared is, can you write it, think of that as a square piece with the 2 there? You can't. If you have like 4x squared, you can, but that's going to be complicated. So what we always do is, if you have a coefficient in front, you first have to factor it out. So let me show Senitu, okay? Let me show you one. So let me take a random example. Would you like to give me an example, or shall I take one random? So let's say 3x squared minus, what do you want to take? I'm going to take a nice, one that works with nice numbers, just to make it look good, say +5, okay? I want to write this in complete square form. Now, as I said, you focus on these two only. Leave the +5, okay? You're trying to make a square out of these two pieces. Now, you can't do it with a 3 in front. So the first thing you have to do is factor that 3 out of these two terms, regardless whether it is actually a factor or not. Now, luckily here, 6 has 3 in it. But even if you had like 5x there, you would forcefully have to take a 3 out. So I'll show you how you do that also. So you take a 3 out here. So the first step is you factor a 3 out of the plus 5. I'm going to write this plus 5 somewhere here, just to make sure that I don't get confused with that. I will bring him in the end. Okay. Now, when I take the 3 out, I get x squared minus 3x. And the plus 5 is there. Next step, 3 is out. I do the perfect square to this x squared minus 3x. So same process. How do I do that? Let me do it different.
X square minus 2x.
Sorry, it is 2x. Yes, thank you. Who else noticed that? Now you have to notice mistakes that I do. Right, now I will turn this into a perfect square. Now you visualize the diagram. X square piece, the 2x piece, you cut it in half, one piece here, one piece here. So that additional piece I have to remove because I am including it in this expression. So this would be x minus 1. How did I get 1? Half of 2. That's 1 square, and I have to minus a 1. I hope this is always minus. What is this minusing one thing? It is, now that piece is there, this piece is there, this piece is there, and that piece, okay, because this piece is included in this. I didn't originally have it, so I have to remove that. That's what I'm doing, minusing the 1. Why is this 1? 1 square is 1. 1 by 1, 1 by 1. This little square is 1 by 1. So 1 times 1 is 1 again. And then the plus 5 is there. And you just have to now clean this up. So this is, if you like, you can, let's multiply everything by 3 here. So this will be 3 x minus 1 squared minus 3 plus 5. Now I brought the 5 near. So finally this looks like, what does this become? I will write it on top here. This is going to be equal to 3 times x minus 1 squared minus 3 plus 5 is plus 2. That's your perfect square. So whenever you have a coefficient in front of the x square term, from those two terms, you take that out and then you do the process. I'll do one more. And then you have to, I think you should copy a couple of these examples down. I will give you time for that. Let's take another example with a coefficient in front of the x square term. Say, let's take an ugly one, okay, like something that doesn't, okay, just watch this. I'll take 2x squared plus 5x minus 9 or something, okay? I'm just writing off the top of my, like, it's just numbers that that come to my mind. So what do? You box these two. Okay, that's what you work with. Equal. So you have to take the 2 out. So you take a 2 out of these two terms. Okay, plus minus 9, just leave it minus 9. Let me just write it here. I'm just distancing the minus 9, just social distancing. So, and what do I get here? I have taken a 2 out. So x squared plus what?
2.5x.
2.5, right? Or I can say 5 divided by 2. Okay, hope that is clear. Then, because when you put, now multiply this back, you will get the original 2x squared plus 5x, you will get it back. Now, I will complete the square, minus 9. I'm going to complete the square now in red. So, this is what? X plus half of 5 by 2 is 5 by 4. 5 by 4 square, and you have to minus 5 by 4 times 5 by 4. That little piece here in the corner is a 5 by 4, 5 quarters by 5 quarters, little piece. So square of 5 by 4. That is 25 over 16. Okay. Done. Now you just have to clean this up. You have done the completing square part. It's done. Now let's clean this up. I'm putting the 2 back in. So that is 2 times x plus 5/4 squared minus 2 times 25 by 16, 2 and 16 cancel, so I get 25/8 minus 9, and then these two numbers you add it, you do the simplification, and then you get a single number there. Hope that is clear. So you can, to add those two, you can use the calculator if you like. That's how you do it. Is that clear? Now let's start copying a few examples down, okay? And that'll give you more exposure to it, and you will get more familiar with it when we do that. Let's go to the note now. I have some examples there. So when we do that, you will understand, okay? So put a topic, changing a quadratic from, first we'll see standard form to factorized form. Then we'll see standard form to complete square form. We are doing both, okay? So let's first start with changing a quadratic from standard form to factorized form, okay? And quickly do this example. This you already know, and you are very familiar with this. So I will let you, I have not given the factorized form. I have left it for you to do.
Is it possible to change a factorized form of a quadratic expression to a complete square form?
Is it possible to change a factorized form into complete square form? Of course.
Yes.
From any form, you can go to another form. So we are first seeing standard form is a normal, like normal form. So how to change from standard form to factorized, standard form to complete square form. Suppose I give you one in factorized form. How do you change back to standard form? You remove the brackets. You multiply the brackets out, you get the standard form. Suppose you want to change a factorized form into complete square form, you first have to go to the standard form and then to this, because you have to have it in the standard form in order to change it into complete square form. Say you are given one in complete square form and you want to change back into standard form, you have to remove all the brackets out and simplify. You will get the standard form. So it, like a fluid, you have to be able to do it from this to that, this to this. It should feel like a fluid. Okay. Oh, I had my, I had my thumbnail switched off. No, I was showing you with my hands, but you didn't see any of that. Okay, Afra.
I saw it.
Huh?
I did see you.
You did?
Yes.
Really?
Yeah.
Okay. I thought I had my thumbnail minimized. Oh, great. Okay. Then, okay, can you copy this? I have the two more examples on the next page. So copy, and you have to change into factorized form. So can someone tell me the factors of the first one? What are the two factors? X. Two factors of 100 that add up to minus 20. You have 10 times 10, you have 25 times 4. Which one works? Yes, minus 10, minus 10. Good. Do you see it is a perfect square then? How do you know it's a perfect square? X minus 10, same side length. You're squaring 1 by the same thing that represents a square. So this is a perfect square. And if you turn this into complete square form, you will see it is a perfect square already. So it's just x minus 10 square. That's how you turn it into complete square form. But let's not do it now here. We are just showing the two factors. Here the two factors are the same. If the two factors are the same, it is a perfect square. And example 2, Senitu is saying x minus 6 and x minus 4. It is not a perfect square. Different side lengths. X minus 4, x minus 6. It's a rectangle. Yeah, that is right. And third example. This is why you learned in the pre-algebra part different ways of factorizing a quadratic. This is a difference between two squares. Oh, is it? Oh. What? X minus 6 and x plus 4? No, that even that won't work. What are the factors here for the second one? Are these factors correct that I have written?
No.
No. If I make it this, is it still right? Still wrong. Then how do I know it is still wrong? You have these two numbers have to multiply into 24 and add up to minus 2. They do add up to minus 2, but they don't multiply into plus 24. This is minus 24 you get. So then what are the factors? This is still wrong. X minus 6 times x plus 4 are not factors of this. They are wrong factors.
There are no factors?
There are no factors. This is an example for a quadratic that you can't write in factorized form. Okay? No factors. You can't write this in factorized form. Cannot write in factorized form. So if you can't find two factors of that number term that add up to the middle coefficient, then you can't factor, simply you can't factorize it. That's it. Okay. Example 3. What are the factors here?
X plus 7, x minus 7.
X plus 7, x minus 7. X plus 7 and x minus 7. It's not a perfect square. But shall I ask you something? This form, which is a standard form, it is already the complete square form too, because you already have x square and just a number. It is already written in complete square form. For that, standard form and the complete square form are the same. All your x's are in a square because it didn't have a x term. Only the x square term it had. So it's already, you have the square term there and the number, hanging number, minus 49. Yes, we don't care about that. Your x is inside a square piece already. So that's just additional something. 2 more you have here. Let me take this down so that you can only say these 2. Now the example 4, you have a coefficient. This is just to, when you have a coefficient in front, it's difficult to write factors at once. You have to do a few steps. So this is why we did this before. So by now you have to know how to do that. So you do that and tell me what the two factors are. So what are the factors of this?
X minus 4/3 and x plus 3/2.
Okay, I'm sure some of you may have gotten this in a different way. Aisha, can you say that again? X minus?
X minus 4/3
And
x plus 3/2.
x plus 3/2. Excuse me. Sorry about that. Some of you may have gotten it this way. 3x minus 4. It's the same thing. 2x plus 3. Okay. Both are correct. Yeah, 3x minus 4, 2x plus 3, Lishan. Yes. Then the last one. At a glance, you can see what that is.
No factors.
No factors. No factors. You can just say no factors, or you can say you can't turn it into factorized form. No factors means you can't write it in factorized form. No factors. Okay. Or can't write it in factorized form. Okay. Then let's look at, can I move on from this if everyone is okay? I hope it's okay.
Yes.
Good, Afra. Next topic, changing a quadratic from standard form to complete square form. Okay, so put that as a topic and let's work out a few examples. Again, I have 5 examples. It's the same 5 examples that you had for the factorized, right? To write as in factorized form, you have the same 5 examples. So the first one, you will have something square, right? Sorry. And you have to put all x's, I mean, in that square. And then a number will come. So what you get there is x minus half of 20 is 10. Because that 20x piece you cut in half. So you get 10 and 10. Like that. But then that, now that's a square. That creates a complete square. But it has a little piece here that we didn't have. So it's included in this expression. So you have to remove it. Minus, that's a 10 by 10 piece. A 10 by 10 piece, that's 100. Minus 100, and then you have the plus, sorry, the plus 100 from the original expression, which gives you, so I'm showing you a middle step here, which gives you, here's your final answer, x minus 10, because this is already a complete square. We saw it already, right? It's a perfect square. Anyway, this expression is a square. You didn't have to do any completion. There was nothing to complete. But I just showed you the process here. I have shown you the process of the steps of completing square. And the second one, again, something square. Oops. What square you get? X minus half of 2 is 1. And then minus, it's a 1 by 1 piece. So 1 times 1 is 1. And then plus 24. It simplifies to x minus 1 squared plus 23. That's your final answer. So here the final answer is this. Maybe I should, okay. Just showing you, I'm just highlighting the final answer. What about example 3? It is already in complete square form. All the x's are in a square. X, there's only one x already in the square term. And then you have the minus 49. Nothing to do. You can say already in CSF. Or you can say it's x squared minus 49 itself. This one. Example 4. There is a 6 in front of the x squared term, which needs to be taken out of the two x, the terms that have x in them. So you take a 6 out first. Let me put a square, oops, a square bracket. So you get x squared plus 1/6 x squared. And let me write the minus 12 a little like that. And then, so I'm doing the simplification horizontally, which is something you should never do. I'm doing it just to, because it's easy for me to type, I'm typing. You have to do your, if you're working it out, you have to go down the page, not across. Then, so the 6 is out, square bracket, let me close the square bracket. Inside the square bracket I will have, here's, I'm completing the square. What square? What am I going to have in the square? X plus, what is half of 1/6? Half of 1/6 is 1/12. And then I have to minus a piece that is 1/12 by 1/12. That is 1/24. And then you have the minus 12 outside. Then let me go down. Okay. Equals.
Miss, isn't 1 over 12 squared 144?
Here's 144. Good. Who else noticed that? How many of you are paying attention? 12 square is 144. And now you take the 6 back into the bracket. So you will get 6 times x plus, not z, x plus 112 square minus, that will simplify to what? 1 over 20, what? 4, 124 minus 12, and then that will be, when you combine the two numbers, you have to do it on your own. Don't copy what I write. Can you combine the two numbers? Minus 124 minus 12. What do you get?
Miss, I don't know where I went wrong, but I get 6x plus 203 squared minus 326 over 27.
Wait. You get 6?
6x plus 203 squared minus 326 over 27.
Can you type it? You get 6x or 6 bracket x in the
6x.
Did you take the 6 into the bracket later and in the end? You don't have to do that.
Oh, really? I thought.
You can leave it like that. Okay. That 6 that you factored out, I mean, you put it back into the big square bracket. You don't have to take it into the square term. Now, you can take that 6 inside the square term. Don't do that. Actually, you shouldn't do that. I'll tell you why. Because I said now each form, from each form, there is something that you can extract, a certain information you can extract about the quadratic. You will be not able to do it if you put the 6 inside. So you're supposed to keep it outside there like that. What is 124th minus 124th minus 12 simplify into?
Uh, 289 over 24.
29 over 24. Good. This
And
is
then it's 289.
289. What?
Yep. Yes, miss.
Where? On top?
Yes.
200?
Minus 289 over 24.
Wow. Okay. 289. That's an ugly fraction. It's okay. 289 over 24. You can use your calculators for any simplification. Don't waste time in the numerical computations. That's why you are allowed to use a calculator. What you are learning here is not how to multiply numbers and how to add fractions, the numerical fractions. That's not what you're doing here. You're focusing on the method of completing square. So for the little computation, you can use the calculator. I think we have one more. This one. So this is the final answer for that. That's how you leave it in that form. Okay.
Miss?
Yes.
Miss, why have you written minus 1 over 144 in the first bracket and then you make it 1 over 24?
Yeah. This one. Because I removed that square bracket. I brought the 6 into the square bracket. The square bracket,
Oh, okay.
right?
Yeah.
Yeah. If anyone has any questions like that, now like what Afra had, how did my 1 over 144 suddenly became 1 over 24 in the next line? Because it's difficult, like you might not see it. I have removed that square bracket by multiplying 6 by the two things in that bracket. So that's how it became 6 times that square thing minus 6 times 1 over 144 gave me 1 over 24. Okay, please make sure you follow every step, you understand every step and every little thing. Okay, and what do we get here? So we are happy with what we have there because the x squared doesn't have a coefficient. We are happy then. X minus half of 6 is 3, and then we have to minus, so that's a 3 by 3 piece, that's 9 minus 9, and plus 2 simplifies to finally x minus 3 square, minus 9 plus 2 is minus 7. So that's the final complete square form. Okay.
Excuse me, Miss.
Yes, Aisha.
Miss, if the coefficient of x was a negative number, it's still the same method that would apply, right?
Still the same method. Let's do one example like that. Can I go to the, if everyone has finished completing this, can I go to the board?
Okay, Miss.
Okay, hope it's okay with everyone. Let me take an example. I mean, okay, so Aisha, can you give me, I mean, you take any, give me an expression. The weirdest, the ugliest looking quadratic, and let's turn it into you, because you know that any quadratic, I told you in the beginning, you give me any quadratic, I can turn it into complete square form. If I give you any quadratic to you, you can turn it into complete square form. So whatever, any coefficient, negative, positive, big numbers, fractions, odd numbers, even doesn't matter. Whatever quadratic you can turn into complete square form. How wonderful, isn't it? So you tell me, okay, you throw me an example with a negative coefficient.
Minus 7x squared.
Wait. Minus 7x squared
Plus 6x.
plus 6x
Minus 144.
minus 144. Okay. Wow. Okay. Strict. Okay. So what do? We focus on the first two terms. Let me show you that these two terms. And x square has a coefficient minus 7. I need to factor it out. So this is going to get me really bad, ugly numbers and fractions, but we can do it. Okay. So here I go to the next line. I'm factoring out a minus 7. The coefficient is minus 7. I factor it out. I factor a minus 7 out. Here's my square bracket. Let me put it like big. I don't need that much in the beginning. And then minus 144. I am factoring the minus 7 out of only the first two terms. Minus 144 is left out of the whole process. In the end only I bring him and simplify with the number. Okay. Okay. So what do I get inside? X squared minus, I hope you're able to work that out, 6 divided by 7, because I took a 7 out, you put that in the denominator, then it will cancel out and give your 6x back. And I put a minus because minus into minus, I need to get a plus 6 back, right? 6x. Hope that step is clear. I simply factored -7 out of the first two terms. You carefully do it. Now I start the completing square process. What do? Again, I only focus on what is in the square bracket. I complete square with those two pieces. Remember the two pieces, the x square piece and the x piece. So the x piece I split into two and fix in the two places. So I'll remember that diagram. So -7, and then I will do this in a different color, the completing square, and I will put the -144 here. I will write the completing square in a different color. So when I fix those two pieces, like, you know, the x square, and half of that piece here, half of that piece here, and then this, if I include it into the square, that square has a side length of x minus half of 6/7. Half of 6/7 is 6/14. Half times 6/7, that is 6/14. Not, yeah, 14, 6/14. Which simplifies to 6/14, simplifies to 3/7. Shall I write 3/7? Half of, like, what I'm doing is this, right? Half times 6/7, half of 6/7. That gives me 3/7. And then that is the side length of that little piece in the corner here. 3/7 by 3/7. So the area of that is 3/7 squared. I have to remove that. I have to subtract square of 3/7. That's 9/49. Done. I'm done with the completing square. Now I just need to clean this up. Clean it up. You know, just make it look nice. Let's take this -7 back into the square bracket. So that gives me -7 x minus, now the square bracket is gone. I'm removing the square bracket. X minus 3/7 square. Minus into minus is plus. 7 times, I'm showing you here, 7 times 9/49 is 9/7. 9/7 minus 144, and these two numbers will add to something. Let me not do that. You can do it with the calculator. And that's what you get. Something, okay, I missed the earlier two sums. Okay, earlier two sums means in the note, right, Umasha? So, okay, let everyone copy this if anyone wants as another example. Okay, you can quickly, I just write this down and try it on your own. Just copy this down. You are completing the square for this. And see whether you are.
Miss, if you want, can we take the -7 also inside the curve brackets?
Yeah, it's fine. You can.
Okay,
But usually, remember, Afra, when we complete the square form, when we turn a quadratic into complete square form, we leave it in, it's a form. The form means a certain format, a template, okay? And we stop from this form. We don't put this inside. You will see why when we discuss what we can extract from this form, what information about the quadratic we can extract out of this form. When you put the 7 back, it's difficult to take that information out. When the 7 is out, when that whatever thing is outside, when it is in this particular form, the secret is, in the square you have to have just x. Now if you put the 7, if you bring the 7 in, you're going to have a coefficient again for the x, and it makes our information extraction a little difficult. So it's okay for now, but don't make it a habit, because you will only be in trouble later. And even in the exam, when they want you to turn a quadratic into complete square form, they tell you, okay, I will show you. They say, Can I write here? They say to turn it, they will give you the form. They will say, write this in the form A, where A is a number, x plus B, where B is a number, square, plus C, where C is a number, in this form. So what is our A here? -7. What is our B here? -3/7. What is our C here? These two together. Okay, Afra?
Yes, miss. I didn't actually put -7 because I just wanted to confirm whether it's actually okay.
Right. Yeah, I mean, it's okay, but we usually don't do that because the useful form is when having the 7 outside, when having that number outside. That is the useful form. So we stop at that point.
Okay, miss. Thank you.
Right, you're welcome. Now let me see whether we have run out of time. I will go back to the note for anyone who couldn't copy this. And you can take a screenshot or whatever if you need to, like from your device. I'm sure from whatever the device you're using, you can either print screen or take a screenshot so you can copy this later. I want to quickly discuss. We have run out. It's 10 now, but I want to quickly discuss. If everyone has finished copying and everything, I will at least leave you with that thought. I will leave you thinking about how these 3 forms are useful. I said they give you certain information about the quadratic. So I want to quickly talk about that. And for next week, this whole week, I want you to be thinking about it. So I will leave you with a couple of questions to ponder upon, okay? So Umasha, can I go back to the board? And again, if anyone missed part of it because your connection dropped or whatever due to reason, I can always send the recording to you. Okay, let me quickly go to, but I will take one of the things that we did here as an example. Let's, for example, take, what is a good one to take? Shall we take, I'm going to take this, x squared plus, okay. Okay, let me go to the board. Okay, I'm showing you a quadratic. X squared plus 6x plus 8. I have given you the quadratic in standard form. Now you know that this expression is just an expression. It's just an expression. Do you know the value of this expression? What's the value of this expression? Do you know the value? What's the value of this expression? Is it 100? Is it 259? How much does it worth as a number? How much is this? What's the value? What is this equal to? This is equal to a number? What can you say to that? Hurry up now, you have to quickly answer.
A equals to 0.
This equals to 0? Why? Who said that? No, we don't know what the value of this is. The value of this depends on the value of x. X, remember this x is 64? Did someone say 64? How? Why?
Yes.
From what basis are you saying that? Why is this equal to 64? Why is this equal to 64? Why? How do you know? If I said, okay, if I give you the expression 1 plus 6 plus 8, look at this expression. This is a numerical expression because all the terms in this expression are numbers. This expression has a value. What's the value of this?
15.
15. This has a value. It is 15. It's not 14. It's not 64. It is not 0. It has a specific exact value. 1 plus 6 plus 8 is 15. But this expression x squared plus 6x plus 8, does that I mean, if I ask you what the value of that is, are you able to tell me what the value of that is? No. Why? Because it has a variable x. It has a letter that represents any number. So the value of this is determined by the value that you put for x. What you can tell me is, if I asked you the question, what is the value of this expression? Your answer should have been, Miss, it doesn't have an exact value, but if x is this much, the value of this would be this much. And if x is that much, the value of this would be this much. The value of this expression depends on how much x is, isn't it? For example, if x is 1, because it has x in it, it's not a numerical expression. If x is 1, if x is 1, then this expression is how much? Would be
15.
15. That's what I gave you earlier, isn't it? 15. This would be, I can't write here, it's 15. But if x is, say, 5, it would be another value. If x is 3.9, it would be another value, depending on what value you take for x, because x can take any value it wants. Remember this we talked about the first day. So the value of this is a varying value. It varies because it depends on what the value of x is. Okay. Now, if I ask you, for what value of x does the value of this become 0? Let me repeat that. If I ask you, when you put what value for x, would the whole expression become 0? The answer to the whole expression becomes 0. Are you able to immediately tell me? Immediately tell me. I'm asking, if you substitute, if x takes what value, would this whole expression's value be equal to 0? Are you able to tell me? Are you able to tell me within a second? Are you? Just answer me. Are you able to or not? You can take some time. Let's put 1 and see. No, it doesn't work. But let's put 3 and see. No, it doesn't
-4, -2.
-4 and -2. How were you able to do that? If you write this expression in the factorized form, remember the factorized form of this is x plus 4, x minus 2. It's the same expression written in a different form. Now it is easy to see for what value of x this would become 0. If you put 2 for x or -4 for x. This is what you do when you solve the equation. So actually the question I asked was this. It is same as asking you to solve the equation x squared plus 6 plus 8 is equal to 0. So when you solve a quadratic equation, that's what you are doing. You are figuring out for what value of x does the expression value become 0. Okay. And here's another question that I can ask. So this form becomes useful to answer a question like that. For what value of x does this whole expression the value of that becomes 0? Here's another question. What if I ask you again? I'm taking.
Miss?
Yes.
Shouldn't it be x plus 2?
Yeah, it's x plus 2. X plus 2. That's a mistake. But you got the concept, right? Once you write in the factorized form, it's x plus 4 and x plus 2. So once you have written the expression in factorized form, you can immediately say that for these values for x, the value of the expression would be 0. Okay, because 0 is a important point, right? When is this whole expression become 0? It becomes of no value. It's when x equals -4 and when x equals -2. Because if you substitute -2 here, this becomes 0. 0 times whatever is 0. Or if you put -4 here, that becomes 0, and 0 into whatever is 0. So those are the only two values that would, for x, that would make the whole expression's value 0. Similarly, if I ask you, now you know that when you put different values for x, you get different values for the expression. If I ask you, if I ask you, for what value of x, here's my question now, for what value of x, for what value of x, of, I can't write there, here's my f, that's off, I have a dead spot in the middle of my screen, I can't write there. For what value of x would the expression, whole expression, have the smallest value? Are you able to answer that? For what value of x would this expression have the smallest value? How are you going to even think about that? Or for what value of of x, where's my x? For what value of x would this expression has the highest value? By plugging in what value for x can I maximize this or minimize this? You understand my question? So I will leave you with that. Just think about, how do you find that? Do you actually plug in different values and just see where it's going? Is it even possible to find? When I put what value, if I plug in what number for x, would I get the highest possible value for this expression or the lowest possible value for this expression? Okay, I want you to think about that. I will leave you with that. We've gone past the time. So as I said, those forms, those different forms become useful in answering questions like that. Okay, that's why we learn those forms. So I hope you were all able to copy everything down. So I will start this discussion from exactly where I stopped with that question. And I will send you, there is homework. You need to practice, you need to practice